All right, we are the University PLA Recycling Group. My name is Josephine Bowden. I'm a mechanical engineer.
I'm Stephanie Benavides. I'm an electrical engineer.
And I'm Connor Murphy, and I'm a mechanical engineer.
So this is an overview of our presentation today. We're going to walk you through our initial design concepts, the final design, some technical details, and then finally a few analysis of our project. So the initial problem. About 33% of 3D print material becomes waste. UC Berkeley, for their engineering, estimates that they create about 600 pounds of PLA waste per year. That's equivalent to 272 rolls of PLA. The amount can vary, especially per college. So supports, failed prints, supports, and projects that you no longer need that get tossed once they're graded, those can all attribute to the amount of PLA waste, which means universities have a few options. They can throw the waste away, recycle it in-house, or ship it to be recycled for a discount on future rolls. However, commercial machines cost anywhere from $30,000 to $150,000 for the extrusion mechanism alone. Downstream drawing and cooling costs, downstream cooling and drawing equipment costs an upwards of $30,000. If a university has a variable amount of scrap that they're outputting and they're not hitting that 600 pounds, this is a massive investment for the college to make, especially if they don't know if they're going to make back the money that they've invested into this machine. So this project takes a look at the extruder portion of an affordable PLA recycling system for a university market.
So the initial design of a extruder is you have your hopper, where obviously you're loading your material. Then you have your motor that's going to be through some form of power conversion, transfer power to your auger, which is going to push your material down your barrel into your pumping section and through your heater, so that way by the time it gets to your extruder or nozzle, it extrudes at the right size, and then there's going to be some cooling fans that cools down at the right rate and gets your right diameter at the end. For ours, we have the nozzle at the very front, we have the barrel, then we have our auger. We have the auger inside, and the nozzle's main purpose is to make sure that you're allowed to get your needed pressure in order to press your material out the hole in the front. The barrel is just intended to be able to hold the material while it's being pushed down hole through your auger, and then your gearbox is to both reduce your speed of your motor and also ensure that you have the required torque. Our design specifically on having easy repairs and also making sure it was affordable, because obviously if we're selling it to universities, we don't want it to be outrageously expensive, as well as it to have a safety and shut off point. So when it gets to a certain temperature, it'll turn off, and when it gets back down, it'll turn on, so it maintains the needed temperature. On our prototype, we did rapid insulation, but we had it, and we would use it on a final design affordability. Joseph will talk about that more later. And for the easy repairs, it's all out in the open. There's no panels or whatever you have to take off. It's pretty easy to change out different parts.
The main electrical objective for the extruder is to heat the barrel to 180 to 220 degrees Celsius, which is the temperature range at which PLA melts. The system pictured here consists of a 24-volt 10-amp power supply, a boost converter, a MOSFET mounted to a MOS module, and two band heaters rated 380 watts, 110 volts. The main objectives for the temperature control system are to maintain the temperature of 180 to 220 degrees Celsius using a microcontroller, to display the temperature to a monitor, to turn off the heaters if the temperature exceeds 220 degrees and display a high temperature warning to the monitor, and to turn the heater back on once the temperature drops below 220 degrees and to clear the monitor of the high temperature warning. The temperature control system, pictured here, features a 12-volt, 1-amp power, a voltage regulator, an Arduino Nano, a thermocouple, a converter, an LED monitor, and an amplifier connected to the MOSFET of the heater system. So in order to verify the accuracy of the temperature displayed on the LED monitor, I've connected a thermocouple to a multimeter and placed it on the heater in the same location as the thermocouple connected to the LED monitor. As you can see in this picture, both the multimeter and the LED monitor display a temperature of 160.5 degrees, confirming that the LED display is showing the correct temperature without delay. This is a video of our extruder during testing. The Recicler is extruding from the nozzle, as you can see, and the temperature of the heaters stays stable right about 210 degrees, as you can see on the monitor. So this is actually the PLA that we were able to extrude. It's all one continuous piece.
It's a lot thinner than it should be because, as you can see on this end, it's quite a bit thicker. It doesn't have the cooling or drying system implemented yet, so the weight of this PLA drags and it makes this much thinner. But we were able to get a very long continuous piece during our testing phase.
For the final design, we would change up the bracket that holds up the motor. We would add a box for the electrical components. Copper would be made of an acrylic sheet attached with high temp silicone. We would increase the overall length of our barrel and auger to increase our heating section, so that way we could get a higher flow rate. The nozzle we would keep the same. It worked as intended. If it's a 2mm hole, when it's being drawn or pulled, it will reduce its diameter down to the targeted 1.75.
So as you can see on this block diagram, the heater system and the temperature control system are connected by the MOSFET. The 24-volt 10-amp power supply is connected to the boost converter. In order to determine the output voltage for the boost converter, I considered two factors. First, minimum voltage necessary for the band heaters to output a temperature within the acceptable range of 180 to 200. I found that at 37 volts, 1 amp, the heaters output a temperature of 200 degrees Celsius. I also considered the drain to source breakdown voltage of the MOSFET, which is 55 volts. So I knew that the output of the boost converter needed to be in that range, 37 to 55 volts. I have it set right now to 45 volts, and I measured about 3 amps outputting from the boost converter. With these numbers, the temperature stabilizes at right about 210 degrees while testing, which is well within that range. As you can also see from this diagram, the thermocoupler is attached to the band heaters and connected to a converter, which sends the temperature information to the Arduino and then displays it on the monitor. When the Arduino detects a temperature greater than 220 degrees, it activates the MOSFET via an amplifier. The amplifier's input is a digital pin on the Arduino, and its output is the gate of the MOSFET. When the MOSFET is activated, the band heaters turn off and a high temperature warning is displayed on the monitor. And when a temperature less than 220 degrees is detected, it deactivates the MOSFET, which turns the heaters back on and clears the monitor of the high temperature warning.
All right, so we did a brief economic analysis of this project. Since we don't have the entire system, we made everything. However, we did make the most expensive part of the system. So these costs were analyzed for that 600 pounds of scraps from our earlier example for a 15-year evaluation period with an interest rate of 15%. The 15-year evaluation period was chosen because we are confident that within the maintenance budget we have set, every single part in this system can be cycled fully, creating basically an entirely new extruder, extending its lifetime. We don't want to say infinitely. However, all of these parts, as Connor mentioned earlier, are easily achievable. So the initial machine cost came out to about $260, and the yearly maintenance that this entire project can be cycled in is $60. Based on an estimate of 272 rolls of PLA that are being recycled and or sent in for a discount at $20 per roll, outsourcing the recycling saves a university about $639.20. This is based off of a 10% discount per 1 kilogram of usable filament. This is based off of a US-based company in Missouri. It is the closest geologically to us. The majority of other recycling facilities are in Europe. For the recycling machine, the cost saved on those 272 rolls is $6,392. And evaluating these costs over that 15-year period with a 15% interest rate, we get an equivalent unified annual worth for outsourcing to be a benefit of $639.20 per year. And for the recycling machine, $6,287.54 approximately per year. Now, this is obviously a much more affordable option for university, especially if they have a variable amount of scraps, like we mentioned earlier. Even if they are staying under 600 pounds of scraps, this number is going to scale pretty much the same with the price for the outsourced recycling. And this is also based on the assumption that the recycling facility is going to cover the shipping for shipments of over 2 kilograms, which is what a lot of the international do. We were not able to find any information for the US-based one on how they handle shipping. However, when if you want to ship a package that's about 2 kilograms, you need a generally large box because PLA scraps are high volume, and it comes out to about $24 per 16 pounds of filament that you're sending in, for a return of about $16 in discounts. So that was not even considered for this project because you would spend more money shipping these scraps in than you would get back. An environmental analysis, recycling PLA offers some significant advantages to producing the new filament. Throwing scraps away just means that we need to mine and refine more material. Life cycle analysis shows that recycling the PLA filament requires a lot less energy-intensive processes than manufacturing the filament. Extraction, refining, processing, those all involve energy-intensive processes like high-temperature treatments and chemical reactions, whereas recycling the PLA involves less energy-intensive methods like mechanical reprocessing to produce our filament for this prototype. We hand ground PLA scraps. So while it was not fun for us, a machine would be able to do that with a lot less energy. It also leads to fewer carbon dioxide equivalent emissions. And recycling in-house cuts out the transportation emissions compared to outsourcing that recycling. And it also diverts PLA wastes from landfills, which introduces it back into the production cycle, which minimizes pollution, conserves valuable resources, and leads to a more sustainable and circular economy.
For the future work, we would need to, or whoever was to work on it in the future would need to design a drawing system for the extruded PLA. They would need to design a grinding system to be able to get it small enough to fit inside of our extruder. They would need to test if the recycled PLA meets industry standards, and then they put to more accurately control the temperature, so that way it's not going up, turn off, on, off. It would gradually adjust the temperature accordingly.
Questions?
So one of the big problems with using recycled materials is you really don't know what happened during the initial processing. So I noticed on your last slide, you said testing this material. Do you guys anticipate being able to do that for your final report?
No, we had enough material hand clip, like we cut it apart with edge clippers and then put it into a blender, which did not survive the process. So we had about enough filament scraps for this. And that was maybe like 6 hours of manually doing that. So we do not have enough filament to even test at this point.
How do you determine size of components, like the motor, stuff like that?
We initially wrote a code to test a bunch of different variables, such as the spindle speed and the viscosity, and those were our major considerations. So once we had a rough idea of what the torque was going to look like, we selected a motor that we were entirely sure would be able to handle that. And then for the auger and the barrel, that was based off of basically what was available to us. And that's basically how we decided everything else, is looking at the pressure that was generated inside the barrel based on its geometry. There are a lot of standard equations for extruders. So once we knew some of the physical components, we could size the rest correctly.
So when you guys said that that this is actually the most expensive part of it, you just considered like what you saw on the, but like actually like if you know the standards, like what are the plus and minus of the diameter of the filament that you can use until your nozzle clog. They actually control in between cooling and the feeding is actually the most expensive, but not the heater itself. Like the heater is cheap, like the control that connects those is actually expensive, because like you actually have to be able to spool at the same time that you're tracking what's your diameter, at the same time that you actually feed into the PID that's actually going to change the temperature there. So like it's actually the thing that's expensive, not the heater itself. The heater is just heater.
Yeah, the heater is just the heater, but the major issue is the auger. That is one of in the standard, like, I got a picture of it back here. In this type of machinery, it is the auger that is the most expensive part, which is why we wanted to go with standard. We got the auger taken care of. It was actually the heating stuff and the electrical that was the most expensive. Which was kind of the goal of this project, as a single screw auger should not be nearly as expensive as it is for one of these machines. There are even desktop extruders that are in that, I think they're around $5,000, where the auger is the most expensive part, and that's thousands of dollars. We got this auger in a pack of 3 for $18, and it functioned. So the biggest part of this project was finding a more affordable version of the auger and then sizing the rest of our parts around that.
I think we have time for one quick question.
I was just wondering if you took into account the feed rate of the PLA in the hopper, like at what rate it's going in. Do you think that would have any influence on the final quality of the PLA?
When we were running our tests, it did have an impact on it. But once it got built up inside, there's enough, the pumping section is large enough that there is non-melted PLA in there that's pushing up against it. And so the front or neck where the heaters are is what is actually melted. And so it kept a continuous flow once it got going. Yeah, once it builds up, it was pretty full, and we didn't necessarily have any issues with filling it up. We didn't have a hopper when we tested it, and it ran without any issues.
We set the spindle speed to 35 RPMs just so we wouldn't have to worry about that. And as you can see from the video, it's extruding actually a lot faster than we had calculated it. It was going to be about 2 millimeters per second. And in that 25 second video, we ended up with a thicker portion than what we wanted. So with the drawing system, it would be well over that rate.
Thank you all.